Hi, good afternoon, everyone. My name is Omer Tariq, and today I'll be presenting our recent research on EmoHEAL, a fusion-based framework for emotion recognition using wearable sensors. This work is a part of larger effort to improve the accuracy and efficiency of emotion detection, particularly in real-time applications using wearable devices. These are the contents of our discussion that I will be discussing for the next 12 minutes. I'll introduce our research problem. We'll discuss some recent work, the motivation behind our own proposed methodology, the comparative analysis and results, and then I will discuss the summary and conclusion. Let's start by looking at the motivation behind this research. Emotion recognition plays a critical role in various fields, from healthcare to human-computer interaction and artificial intelligence. Advances in wearable sensor technology allows for continuous real-time monitoring. Devices like fitness trackers and medical IoT wearables are key examples where emotion recognition can play a role in tracking the health status and improving the patient care. Effective computing emphasizes the integration of AI and interpret and respond to human emotions, and it's becoming more prominent across various industries. The challenge is bringing advanced deep learning models to resource-constrained IoT devices, which limits their real-time capabilities. Problem statement. One of the primary issues with emotion recognition systems is the high variability and noise in sensor data. This noise significantly impacts the accuracy and performance of models, especially when dealing with physiological signals. Another challenge is balancing the complexity and efficiency. While many deep learning models excel at analyzing complex data, they are often too resource-intensive for IoT devices and edge deployment. To address these issues, there is a growing need for lightweight and efficient models that can perform emotion recognition in real time on low-constraint, low-resource devices. I'll discuss some recent work that has used the traditional approaches regarding emotion recognition. Zhao et al. Used adaptive filters to reduce noise and physiological signals, extracting features from the time, frequency, and nonlinear domains. These were classified using support vector machine algorithm after feature selection. And Zhu worked on EEG signals, extracting features from time, frequency, and space domains. They combined the gradient boosting decision tree, random forest, and SVM using a model stacking approach. The limitations of these handcrafted features, including difficulty in capturing deep relationships and nonlinear patterns, prompting a shift to deep learning methods that offer better representation and scalability. Now I will discuss our baseline, that is the research proposed by K.Yang, where they evaluated their emotion recognition system using the K-EmoCon dataset and Ascertain dataset. The two-class arousal classification using the K-EmoCon dataset achieved a mean accuracy of 71.37, and while the two-class valence classification reached to 69.11%. This is on K-EmoCon dataset. And for Ascertain, their arousal and valence accuracies are 71.79 and 69.11. The figure on the right shows the overall architecture of their proposed framework. It includes the pre-processing of signals like BVB, EDA, SKT, skin temperature through convolutional front ends. This is followed by the conformer encoder for multi-signal fusion and feature extraction. Our proposed research aims to develop a lightweight and efficient deep learning model capable of real-time emotion recognition. By addressing the challenges of noise, computational complexity, and performance, the study seeks to contribute to more scalable and practical emotion recognition systems. This is the pipeline of our proposed model for processing that is being evaluated on K-EmoCon dataset for emotion recognition. The raw sensor data undergoes initial binarization and resampling to ensure the signals are pre-processed uniformly across different channels. To enhance the robustness of model and the random Gaussian noise with a standard deviation of 0.01 is being added. This helps simulate real-world noise in the sensor data and trains the model to handle variability and generalization. The core of the pipeline involves a hybrid deep learning architecture that combines a temporal convolutional network with integrated channel and special attention modules, and a gated recurrent unit. The model performance is evaluated through a group K-fold cross-validation, and several metrics are considered, including the accuracy, precision, recall, F1 score, as well as, additionally, we computed the computational complexity of the models and their flops, which is the floating point operations. I will briefly discuss the data set that we have, our proposed model is being evaluated on. The K-EmoCon dataset is a multi-model sensor dataset specifically designed for emotion recognition. It integrates data from multiple physiological sensors to capture emotional responses. The dataset includes 32 participants who took part in 10-minute session. For our proposed research, we used the wrist sensors, which is derived from the, which we collected from the Empatica E4 wristband device, measuring the electrodermal activity, the blood volume pulse, the skin temperature, heart rate, and accelerometer data. Emotion annotations were recorded every 5 seconds to provide a detailed temporal mapping of emotional states. Additionally, the dataset includes self-reports, partner assessments, and external evaluations to ensure a multifaceted view of participants' emotional responses. Now let's discuss our framework. The EmoHEAL framework uses data from various sensors attached to a wearable sensor, as discussed previously. The collected sensor data is fed to a deep learning pipeline where each data is processed by individual temporal convolutional blocks. These TCNs are effective at capturing temporal patterns in sequential data. After the feature extraction, the outputs from each TCN blocks are passed through a gated recurrent unit for fusion. The GRU layers are designed to capture dependencies across multiple signals, enabling the model to effectively classify emotions based on combined temporal features of all inputs. The combination of this framework, where we have different TCN blocks for each data modality and GRU fusion, enables a pipeline to learn both temporal and cross-signal features, enhancing the model's ability to accurately classify different emotional states. Let's discuss deeply about the TCN network. The TCN architecture is designed to process sequential data by applying dilated causal convolutions. These allow the network to capture long-range dependencies in the input sequence while preserving the order of the data. The dilated causal convolution expands the receptive field without increasing the computational cost, ensuring that the network can analyze data at different time scales while maintaining causal dependencies. The residual connections are also applied to improve the flow of gradients throughout the network during backpropagation. This helps prevent the vanishing gradient problem and ensures more effective training for deep networks. The causal structure ensures that each output is dependent only on the past and the present inputs, which is essential for real-time applications like emotion recognition, where predictions must not be influenced by future data points. So, each DCN block has this architecture where each DCN block is enhanced by the convolution block attention module. This module introduces attention mechanism that helps the model focus on most important features in both the channel and spatial dimensions. The TCN block consists of 3 sequential temporal blocks, each responsible for capturing temporal dependencies in the input data. These blocks are crucial for processing sequential signals. The channel attention mechanism focuses on emphasizing the most important features across different channels, making sure that the model prioritizes the most relevant physiological signals for emotion recognition. And after passing the features from the channel attention, the spatial attention helps the model concentrate on the most relevant spatial regions of the input data, ensuring that it is not distracted by the irrelevant parts of the signals. The TCN outputs from multiple signal channels are concatenated to form a comprehensive feature vector. This step ensures that all important features from each sensor modality are combined. The concatenated outputs are passed through two linear layers with ReLU activation to introduce nonlinearity. The resulting feature vector is unsqueezed, which means it is reshaped to fit the sequence dimensions expected by the GRU, preparing for processing temporal dependencies. The GRU processes the sequential data capturing long-term dependencies between different timestamps. This is critical for emotion recognitions, as emotions unfold over time, requiring understanding of temporal context. The dropout is also applied to prevent overfitting and improve the generalization. Our training framework use cross entropy as loss function, and we used Atom Optimizer with learning rate scheduler is chosen for its efficiency. We used the early stopping is applied based on the validation performance. The batch size is set to 32 to balance memory efficiency and gradient estimation. And as we discussed, we used group K fold, K is equal to 4 is used to ensure the model generalizes well across different data subsets. And this method splits the data set into 4 folds, rotating training and validation sets to evaluate the performance more efficiently. This is the table for our evaluation metrics. This table compares multiple deep learning models based on arousal accuracy using various methods such as mean accuracy, loss, precision, recall, and F1 score. As we can see that our proposed model where the TCN is integrated with channel and special attention and Fusion GRU model achieves the highest mean accuracy and performs the best in terms of mean loss, making a strong candidate for this task. Other models also demonstrate competitive accuracy. Moreover, we can see that the parameters and flops for our proposed model show a very competitive balance between accuracy and efficiency, making it suitable for real-time emotion classification. The table summarizes the performance of our proposed model across two classification tasks, arousal and balance. For arousal task, where we classify emotions based on arousal levels, the model achieved an accuracy of 73.04 to demonstrate a solid level of performance in distinguishing between different arousal states. For balance tasks, which involve distinguishing between positive and negative emotional states, the model performed exceptionally well, achieving a mean accuracy of 93.95. Let's discuss the summary. We developed a deep learning model for real-time emotion recognition and addresses the challenges related to sensor noise and computational efficiency. We leveraged multimodal physiological sensor data from the KMON dataset for risk sensors and implemented a hybrid TCN-based GRU architecture for enhanced performance. We have achieved improved accuracy with efficient computational resources usage as compared to baseline. And for future work, we will work on the model refinement and broader deployment on wearable devices. These are the details of the authors. If you have any questions, please, and these are the references. If you have any questions, please feel free to ask. Thank you.